In this next subsection, I want to talk about a lower bound. That is a provable guarantee that no algorithm in a certain class of algorithms can ever perform better than a certain bound, a certain minimal barrier that we cannot break through. And that's one of the core features in algorithm theory, that you're not only able to construct and engineer algorithms that are useful to solve problems in practice, but also you can show often very rigorously what their limits are. And this is the goal of this section, to show on a simple example, namely the world of sorting, how such a lower bound proof can look like, and also what we can do about it. With that, let's get started on the comparison-based model. Again, I think this topic is something that many of you will have seen, but maybe not quite from the rigorous perspective. So let's spend some time on this. A lower bound is a mathematical proof that no algorithm can do better. So it's essentially a statement about all algorithms. And these are very hard to prove. If you remember from the proof techniques, this is a statement that is all quantified over all algorithms. It's a very powerful concept because it's an impossibility result that is proven rigorously mathematically. So there's no wriggle way, there's no way to discuss with this. I'd like to compare it with conservation of energy principles in physics, but it's usually much stronger. I mentioned this before. Usually we can prove stronger lower bound than what the fundamental limits in physics mean for machines. Usually our, combustion machines reach limits much earlier than the conservation of energy would predict. In computer science, we're often much closer in that we can, for many problems, achieve something that is at least asymptotically the same as the lower bound. We find an algorithm that has the cost predicted by the lower bound up to constant factors and up to the fact that we have to do to restrict our attention to large inputs. But subject to these restrictions, these are optimal algorithms. I'm not the greatest fan of using this term here because optimal can mean many different things for different people. But it's a useful concept to to sell your results probably. That's what it's most useful for. As I said, it's a statement about all algorithms, so we must precisely capture what this means. What is all algorithms? We already know one way to do it. Any formal model of computation is suitable to do this. Any formal model of computation of computers defines a class of algorithms. But it turns out that the RAM model is fairly powerful, and so it's hard to prove lower bounds for it. It's not impossible, and people do this. This is an active field of research. But for today and for here, we want to look at a more restricted model where the lower bound proofs are simpler. And this restricted model is the comparison model. Sometimes people don't make this very explicit, so I want to make this very, very explicit. It is a model of computation. It is a model of a computer that you can have in your mind, but we cannot really build this type of computer. It's a purely theoretical abstraction, but one that will be essential in the proof and what follows in the next subsection. So it's don't mistake this as a blueprint to build the next generation of Pentium whatever or Intel Core i whatsoever. This is a mathematical abstraction. So our machine is a box, and we have a large array of elements that we try to sort in our case, but the comparison model doesn't care much. It's you can work with these elements in any way you like. And essentially this array is filled with objects of different sizes. And the algorithm has the machine has a balance where you can put two elements and you can compare them. And the outcome is either less, equal, or greater. And that's all you can really know about the elements that you're working with. They don't have colors, they're not numbers that you can divide. The abstraction here is the only thing you know and the only thing you can do with these elements is compare them. If you have to, you can say which one is smaller, which one is bigger. The other thing is you can move elements around, so you can decide to swap two elements and then you just exchange them in the array. So we can do comparisons, we can do swaps, and pretty much that's it. It's a very simple model of computation. As I said, it's overly restrictive. You wouldn't be able to do much beyond sorting with it. A few other related problems. But that's not the point. The point is to have a simple model that captures the essence of the sorting problem and then prove lower bounds. So let's continue with this. It makes very few assumptions on the objects that we're sorting. As I said, you can only compare them, which is weird if you want to program with it. Well, not too weird, because merge sort and quicksort actually just use the element in that way. But this is what makes the model helpful for lower bounds, because it's fairly general. It doesn't make many assumptions. That means it applies to many different things. And what makes this problem, this model nice for analyzing it is that every algorithm can be represented by a single relatively easy to understand object, and that's the so-called decision tree. Now this is a tree, and I will show an example on the next slide in a second, but I want to briefly explain what it looks like. We only model the comparisons that our algorithm does. So remember, one decision tree means one algorithm. There's a one-to-one correspondence between these. So we model only the comparisons. We ignore the data movement. The actual algorithm has to swap elements around. The decision tree completely ignores this. The nodes in the decision tree are the actual comparisons that the algorithm does. And this could mean, it could say we compare the element at position 17 with the element at position 42. And that can have a couple of different outcomes, smaller, equal, or greater. And that's what a single node in the comparison tree encodes. And then the next comparison that the algorithm does after these can depend on what was the outcome. So if this is your node, you can have different outcomes, less, equal, greater. And the next comparison is here in these child nodes, and that comparison can depend on what that comparison gave as a result. All right, and if you continue doing this, you eventually reach a leaf node that doesn't have any further children. And these leaf nodes correspond to an input permutation. So one important aspect of this model is, because we don't assume anything about the objects that we are given, all that is really relevant is to learn which of the objects is the smallest, what's the second smallest, what's the third smallest. In other words, what is the order of these objects in sorted order? How would I have to rearrange them? And learning this permutation is what decision trees encode. If you restrict yourself to permutations, that implicitly means we will never use this equal branch, because permutations imply that all elements are distinct. That's a minor assumption here that makes life a little cleaner, but it's not a vital restriction. You can extend the comparison model to handle these cases as well. So here's an example of a comparison tree. As promised, this is, again, a specific algorithm on inputs of size 3 to not make it too big. There's 6 different permutations of the numbers of 3 objects. And because we don't assume anything about the objects, we might as well take the integers 1 up through n. We just are not allowed to make use of that knowledge. So if we start out, the algorithm doesn't know anything, and any of these 6 permutations is possible to be the permutation that the input is in. Now the algorithm decides to first compare the first and the second position in the array. If the first position is smaller, it decides to make another comparison, namely the second and third. So remember, we start at 0. So if we follow this left branch, if the input is such that both of these comparisons turn out as less, then the input must have been already in sorted order. That's one of the possible outcomes. And you see, whenever you do a comparison, there's a certain number of permutations that are currently compatible with your state of knowledge, what you currently have learned about the input. And then adding the next comparison splits this set of permutations into 2 parts. And as soon as that part is a single permutation, you have learned the exact order of the input. And that's all we need for sorting. You could then just move all the elements around to apply the inverse permutation, and then the input is sorted. I hope this example makes it a little more clear what these comparison trees look like. And remember, you have a different comparison tree for every input size. Now, what can we say about these trees? If we execute the algorithm on a specific input, so maybe this is something to note here. One comparison tree corresponds to one algorithm and one input size, one n. All right. If I now were to execute this algorithm on an input of that size, I get a single execution. And that's what this is talking about. So one execution means following one path in this comparison tree. And the leaf that I reach encodes the input permutation. On every step I do, in every node that I pass through, I do one comparison. So that means the length of this execution path is the cost of that execution. And the height of the comparison tree is the longest such path. So that's the worst case number of comparisons. Okay. So in our case, the height of this tree is, we defined it as the number of edges, 1, 2, 3. And that's also the number of comparisons that this algorithm does in the worst case. Any of these inputs is the worst case, where you do 3 comparisons. Next observation is comparison trees are binary trees in this model, where the outcome is one of 2 things. And that means, remember, we talked about this when we discussed binary heaps. Even if we make all the levels full from the top, we do need that many levels to get to a certain number of nodes. So if we have L leaves at the bottom, it turns out we need a height that is log of L rounded up. And finally, the last observation is, if you want a comparison tree for sorting, then you need all these all the permutations that are possible for an input to be in as leaves. That is n factorial leaves. And so the height is this log of n factorial, which is asymptotically equivalent to n log n. Okay? So wrapping up, any decision tree, start a step before that, any comparison-based sorting algorithm corresponds to one decision tree per input size. Any such decision tree for a size n has to have n factorial leaves, and it has to have size height at least log of that, which is n log n up to lower order terms. So the height of this comparison tree must be n log n, and the height of the comparison tree is the worst case number of comparisons of that algorithm. So what we've proven is that this second part here, so that's not what I wanted to say. I haven't written down the statement of the lower bound, which maybe we should. So this is the conclusion from these two things. So any comparison-based sorting algorithm needs n log n comparisons in the worst case. And well, here we don't have a notation for greater equal, but let me be more precise. Let's write log n factorial here to make it easier. Any comparison-based sorting algorithm needs at least log n factorial comparisons in the worst case, and that is tilde n log n. So we could try to squeeze that in here to make it complete. And let's see. That is the lower bound, the comparison-based lower bound for sorting. And we've seen that merge sort essentially achieves this. We didn't really analyze this in detail. We analyzed the number of element accesses, where the constant factor was slightly different. If you revisit the analysis and look at the number of comparisons you do in a merging step, that's linear in the size of the output of the merge, and hence we get this bound for merge sort. And so merge sort is an asymptotically comparison optimal algorithm, even with the right leading constant. What's less clear is about these low order terms. You can actually do with a good deal less than n log n comparisons. You could, in principle, go down to something like n log n minus 1.4n. And it's a long-standing open problem in computer science whether you can find a sorting algorithm that achieves this asymptotic number of comparisons in the worst case. There's essentially been no progress since the early 60s on this question, with some very recent attempts which haven't fully been reviewed yet. But yeah, this is, as of yet, it's an open standing problem in the theory of the problem. I want to briefly see if you were following this. And so to test your understanding about the concept of decision trees, let's do this question. And I probably should show you this slide so that you can compare with this. So the question is, just for this input size, is this a tree that's best possible in the worst case, or is there any way we can sort 3 elements more efficiently? So let's see what you think. Okay, results are trickling in. Maybe time to switch to that screen. Okay. We were at 39 for the first question, so maybe I'll leave it open for a few more seconds. Okay, because it's so clear-cut, you should see the results now. Yep. So there's a large fraction of you who are saying, yes, this is optimal, and this is correct. And the reason for that is, well, we have to look at the number of leaves. There are 6 leaves in this case. So we take the logarithm of that. That's a number between 2 and 3. We can't really do sorting with 2.5 comparisons in the worst case. That won't work. So the best we can do is round up. And that means 3 comparisons are necessary to sort 3 elements. And this algorithm also shows that this is sufficient because this is one way to do it. There are others which are equally good. So yes, this is an example of an optimal, worst case optimal sorting method for 3 elements. With that exciting statement, I'll conclude the section on the lower bound.